And we are live. Hello there. If you are tuning in right now, then you have tuned in to the McMaster Competitive Programming Week 8 training contest stream. So this training contest is part of the training material that we started releasing in early August. And this is actually the last week of it. And in this week, we'll be covering network flow and geometry. However, do know network flow and geometry are like fairly difficult topics to the extent that they don't really occur much on HackerRank. So you won't have to worry about knowing network flow or geometry to answer the questions on the contest today. So I wouldn't fret too much about that. But our contest will start in 12 minutes. I hope everybody is all signed up. And I should say too, so this is the last contest we're having in this format. So in the next coming weeks, you can hopefully we'll see some events with like different formats, and we'll try out some new things. Like we haven't scheduled a date for it yet, but at some point we should be holding our data structures workshop. And one thing we're trying to figure out, and maybe you can give your input in the chat if you have an opinion on this, is whether we want to do our data structures workshop in Python, C++, or both of those languages, or maybe even Java as well, if people are into that. Because we're interested, we did our like our basic like essentials workshop where we went over the basics of Python and the basics of C++, and people surprisingly seemed quite interested in C++, which is actually really good because C++ is sort of the de facto language for competitive programming. It's what the majority of people use, so it's really good if people learn that. It's funny. So you guys all know that we have ICPC every year, and every year at ICPC we normally write it on this website called Caddis. And on Caddis for ICPC, you're allowed to use C++, Python, or Java. And it turns out that they don't actually guarantee that all problems are solvable using Python. So internally, they are running your Python code with PyPy, which can make it like anywhere from like 10 to 100 times faster. But still, uh, PyPy, I don't know, sorry, even with PyPy, it can be like too slow and you might just be out of luck, especially if there's recursion involved, which can really slow things down. Ooh, we have a comment from the chat. It says, CPP for data structure workshop, please. Yeah, honestly, we're kind of leaning towards, we're leaning towards CP++ a bit. I think it's more interesting. Like, most data structure stuff in Python, like, isn't that interesting. Partially because Python is, like, just nice to work with. But I don't know, I think people could learn a lot more from CPP workshop. Although I might do, like, what do you call it? Like a poll or something in the event. Sorry, a poll in, like, the Facebook group. See what people are into. Oh, I hope people like the training content for this week. For the geometry thing, I threw in some old ICPC questions from our region. So our region is like this East Central North America region, and I think our region's questions are pretty hard, like comparatively compared to like some other regions. Um, but like in the past, we've had some interesting geometry problems. Like I think some of the ones I included were one was you're given a pizza, but like instead of being sliced into like regular like pizza slices as you normally slice a pizza, we're gonna take a pizza and like slice it into like rectangular wedges. But of course, like since your pizza is originally still a circle, you're gonna end up with all these weird like lopsided pieces. And I think the goal of the question is you have to figure out how many of these like weird lopsided pieces are beneath a certain size. And it's actually a really interesting geometry problem. You end up needing to figure out how to find what is it, the intersection in area between uh, a circle and an arbitrary like convex polygon, which is really interesting. You have to know like the shoelace formula, and you have to make this insight about breaking down like I don't almost like sorry. There's I don't know. You have to make this insight about looking for these things I call like hills, which are really interesting. But it's a cool problem. I have it posted on the training if you guys want to try it out. That's nifty. And then there's another problem that I posted. It's basically just math. There's like not even that much geometry code. It's just plain math. It was you've got like a pool table and you've got like a few like balls in the pool table, and you have to figure out. If I remember the question correctly, you have to figure out the perfect shot that you could do such that your white ball would hit one ball, knock it into one corner, and hit another ball and knock it into that corner. So it sounds like really hard and complicated, but it's just math, just like straight math. I find like a lot of geometry problems boil down to being like some convex hull thing or like straight math. So I feel like the biggest thing you can do to prep for them is just to practice. Although I guess that holds true for like most of competitive programming. Uh, Now, surprisingly, the other topic for this week, flow, is I'd argue the the algorithms involved in doing flow itself are actually pretty easy to learn. Like you learn like fluid Warshall and like I think it's Euler Carp. So those aren't too bad to learn, and they're really quite applicable. You can use them for like matching problems and for just like normal max flow. But the harder part tends to be applying them because when you apply them in practice, you have to like realize that it's actually a flow problem and figure out how to frame it as a flow problem, which is like where most of the actual difficulty is. Uh, One of my favorite usages, which is like really non-intuitive, and I guess I sort of mentioned this, is the idea of matching. That's the idea where you imagine you have the standard example is you've got like a set of people and you have a set of jobs, and like any particular person can only do like certain jobs. So maybe like let's say I've got people like A, B, C, D, E, and so on, and I've got jobs like 1, 2, 3, 4, 5, and so on. And maybe it's something like person A can do jobs 1 or 2, person B can do jobs like 2, 3, or 4, person C can do jobs 5 and 6, and you want to figure out like the total number of jobs you could get done, given that like one person can only do one job. So a problem like that can actually be solved with flow, which seems weird because you'd wonder like what you're flowing. But the idea is how you construct your graph is you have your source node, you have your sink node, then you have a node for every person who can do work, and you have a node for every job, and you can make like a node of weight one going from every person to every job they can do, and a node of weight one going into each person. And then the idea is if you assign a person to a job, it's effectively like analogous to sending one flow through the network. And then at the end of the day, the total number of flow you can send through the network is the total number of jobs that you can get done. And this is pretty efficient too. So fluid Warsaw, which is pretty slow, I think it guarantees you can run in like your runtime is proportional to the time it takes you to do a DFS, so like linear time times your max flow. So you can run like I guess in like the number of nodes times like the you however like large your solution is would be like your runtime. But that's for fluid Warsaw, which is pretty slow. So if you go and you use like Euler Carp instead, you're actually going to be like a lot faster. So it's like I don't know. So you rarely run into runtime troubles, and it's quite applicable. I quite like it. So 5 minutes left till the contest start. As I said, despite all that I've been talking about, like geometry and network flow, you don't need to know either of those things for the contest today. So don't be freaked out. These are standard hackering questions. I've solved them all last night, so I know they're all doable. And they should be fun. I really like them. Especially there's this one problem. I won't spoil anything yet since the contest hasn't started, but I think it's not terribly hard to solve, but it's really fun. It says like it's a pretty problem. I like pretty problems. I feel like when I do these like up solving before the contest to make sure the questions are okay. If a problem's like really like not pretty, I just drop it. It's like I don't want to like put people through that if it's super gross. So sometimes on Hacker Rank, they're not interesting. They're not even like hard. They're just like big and like gross, and nobody gains anything by doing those problems. I guess unless you really just want to work on your implementation. And I guess to be fair too, normally at least like 2 to 3 questions on ICPC every year are like straight implementation. But I'd argue you could learn implementation while also learning how to do like specific algorithms or other more complicated topics. It's interesting to look at the disconnect between the question content of contests like ICPC and the question content of training sites like Codeforces. For instance, ICPC every year will have probably at least two geometry problems, which are like quite difficult. However, contests like on like things like Codeforces rarely ever have like geometry problems. So if you're training for ICPC, it can be really good to practice actual ICPCs as well. Uh, for that, actually, for a while I've been thinking. I've been very busy lately, just because like it is like, I mean, even with COVID, it's like job applying season and whatnot. But when I'm a little bit less busy, I thought it might be fun to start trying to do like an ICPC every week with people if people are interested in that. If we could drop in like a Google Meet or something and like work through the problems and see how much we can get done. Because like yeah, as I was alluding to, like the best way to prep for ICPCs is really to solve old ICPCs, especially some from our region. Although it can take a while to solve them all. Like I think when I tried to solve ICPCs, it's you can solve like the like at least like half the questions in a reasonable amount of time. But then like after there, it's like it's almost like diminishing returns. Something it's like it takes like exponentially longer to solve each additional problem after the first few. If you get like super stuck on them. Like I think this one time I tried to full solve an ICPC from our region, and I got 9 out of the 10 questions. But I sunk something like 30 hours into it. Now don't let that terrify you. You should not be sinking like 30 hours into a contest. I think there's a point where it becomes like unproductive. If you're sitting on like a single problem for more than like 5 to 10 hours, even that's like insane. I wouldn't even do that. If you're sitting on a problem for more than like 2 to 3 hours, I think it starts to get a bit unproductive. But I guess you can operate at like the I don't know if it's a delay or the time allocation. I don't know how you can operate at like however much time you're comfortable giving each problem. I tend to be like stupidly stubborn, so I'll sit on a problem until I get it. But I think I lose a bit of productivity for that because I'm not doing other problems. Like I think a better way would really be like try a problem, make sure you understand it, chart a few strategies. Once you feel like you've exhausted like everything that immediately came to mind or everything that came to mind after a bit of extra thinking, it's totally okay to like look at the editorial. A good thing if you're stuck but you don't want to have the full solution, you can like read a little bit of the editorial, but then go back to problem solving again and see if you can get it. You don't have to like read the whole thing. But one thing I will say is that if you read the editorial, you have to make sure you actually implement, because it's really easy to look at the editorial and say either like A, like, oh, this is too complicated, I don't want to read it all, or B, read it all and then say, oh, I can easily implement this, and then you don't implement it. It's really easy to think you understand something when you don't actually do it. Like you should definitely actually like implement it in code and make sure it passes. Okay, we're down to our last minute before the contest. Uh, I should mention, as per usual, we are competing today for the prize of an MCP T-shirt, and as per usual, people who've already won a T-shirt, of which there are quite a few now, I can't win an additional T-shirt. So you've got very good odds of winning a T-shirt if you participate. I will put that out there. All right, 40 seconds. You'll see this as a MDT, which is like Mountain Daylight Time. That's because I'm hosting this live stream from Calgary, Alberta, Canada, which is way out west. But fret not, this is 12 to 2 Eastern Time, so it's fully the usual time of our contest. Almost there. And refresh. Okay, and the contest has started. We have 6 questions today. The two easiest questions are worth 10 points. They're pretty like similar in difficulty, I guess, which is why they're worth the same amount of points. So feel free to start on either one and work through them. We'll then proceed to get a little bit harder, but still not too hard. And then even the last ones aren't like terrible, but the last ones are definitely more fun. The very last one in particular is beautiful. I love it. That one's gonna be really fun to solve later. Yeah. I will say the only thing you really need. So pretty much like the first four of these are like some implementation of some form. But the last two are the only ones where you have to know like other things. Like this cut the tree will require some knowledge of graph theory, and Sherlock and Collis will require some knowledge of DP. But the rest are like solvable with implementation, and even like the stuff you need to know if these last two aren't too bad. Like you could figure it out if you don't know it. So I guess to get started, I'm gonna walk through a few problems. The first problem on our contest today is something called breaking the records. So I feel like the first diagram they give you here is a bit confusing. But the idea in this problem is they're going to give you a list of scores, and the idea is that these are the scores for Maria in her college basketball season or something to that effect. And what we want to do for Maria is we want to count whenever she gets a new like highest score or a new lowest score. So for example, if we imagine iterating along this way from left to right, our initial score is 12, and then when we move to 24, I get a new highest score. When I move to 10, I get a new lowest score. And then when I move to 24, my high score was already 24, so nothing happens. So here our answer would be, sorry, the final thing we want to output is like the number of new maximum scores we get, followed by the number of new minimum scores we get. So here we get like 1 and 1. So it's not too bad. We're just going to iterate through and same when we get a new max and same when we get a new min. And they've got like a pretty good diagram here explaining that. Now, if you make it past breaking the records, you'll move on to bill division. So for this one, we've got our two good friends, Anne and Brian, who went out for dinner. And it just so happens that, so Anne and Bill ordered some dinner, but Anne didn't eat one of the items. But we want to make sure the bill's split correctly. So the idea is we want Anne to be charged for all the items except that one item she didn't eat divided by 2. So, for instance, if for dinner we ordered spaghetti, croissants, and beverages, and Anne didn't eat any of the croissants, then we would only charge Anne for the spaghetti and the beverages divided by 2. And how this input looks is they'll give you an array of all the price items. They'll give you an index, so that's like a zero index thing, telling you which item Anne didn't eat. And they'll tell you how much Anne paid. And we want to figure out, like, so we're assuming that Anne already paid some amount, and we want to see if we overcharged Anne. So we just do like the amount we charged her, which is B, minus the actual amount, which is like that we want to charge, which is all the items minus the one item she didn't use divided by 2. So we just compute that. And then there's like a weird edge case where if it turns out that she paid correctly, we just want to print bon appetit instead, since everything is really good. So once again, this problem is not too bad either. This is just implementation. Okay, if you make it past that, you'll move on to a problem called pairs. So this is actually really fun. I won't. This is really similar to another problem that's very popular. So I won't tell you what that problem is because that's like almost too much of a dead giveaway. But the idea is you're given an array and you're given some target value, and you want to figure out how many pairs in your array have a difference equal to that value. So that's very fun. Won't spoil anything for that. Oh, no, this was the one I was mentioning before the contest that I think is just like really pretty. The idea here is you have some toy, and the idea is this toy has a width of h. Sorry, yeah, a width of h. Sorry, I can't speak. A height of h. That would make a lot more sense. Sorry, height of h, width of w, and sorry, and that corresponds to having like h rows and w columns. And these rows and columns are on this 1x1 grid, and in each one of these particular cells in our 1x1 grid, our toy has a given height. And so this ends up forming like this 3D object, like you can see here. And what we want to do in this question is we want to find out the total surface area of this 3D object. So everything on the top, everything on the bottom, and everything on the sides, including these like side parts like inside of the shape, which is fun. So this is a cool problem. I think everyone will enjoy this. We technically we've used this web problem once before because we used this for the first year contest that we'd held in like I forget if it was during like the welcome week thing or even like slightly after that. So if you were in the first year in the welcome week thing, you might have seen this, but I don't think many people solved it, so I've included it again here, especially since I assume everyone's not first years. And if you make it that far, you're going to go into a problem called cut the tree. Now, I really wish I discovered this problem earlier because on an ICPC contest, I think like 2 years ago, there's a problem that had like effectively this idea as a subproblem, and I didn't get the insight at that point, which caused me to my algorithm to be too slow on the ICPC for this. But this problem's nice because it isolates just this one interesting sort of like small problem, and if you can solve this, it'll be really useful in other problems. And so the idea here is you're given some tree, and you're given nodes that have like weights in them effectively. And what we want to do is we're allowed to cut one edge in our tree, and we want the absolute difference of the remaining subtrees to be as small as possible. So when I say the absolute difference of the subtrees, I mean, imagine you cut an edge. Like, let's say we cut this 3, this edge labeled 3 right here. I'd be left with a subtree that contains just this node 6, and a subtree that contains everything else. We call the weight of a subtree the sum of all the nodes in it. So if I cut this 3 here, I'd have one subtree of weight 6, and another subtree of, let's see, 4, 3, 6, 10. Sorry, and another subtree of weight 15, which would be the weight of everything else. And so the difference there, which would be 9, which isn't very good. We can do better than that. Like here we see, the minimum absolute difference is 3. Actually, let's see if we can even find where that is. That will be... not that. Let's see if I can actually find it for you guys. Oh, I guess they say it right here. Oh wait, is this even right? 2. Oh yeah. If we cut this edge 2 right here, then this subtree on top becomes 9, and this subtree down here becomes, let's see, 12. 9 and 12. So you get a difference of 3, which is apparently the smallest we can get. So I will say you can effectively, you don't need too much code to implement this, so don't overthink it. But there's a really clean way of doing it. It's like a very useful thing to know how to do. Okay, and if you make it that far, all right, this final problem is a little bit challenging, but it's really fun. It's called a Sherlock and Cost. And the idea is you're going to build an array, and that array is called A. And you're building this array A under the constraint that A and I, under the constraint that you're given some other array B, and A and I has to be greater than or equal to 1 and less than or equal to B. So effectively, every element in your array that you're allowed to build is like bounded between 1 and some value. And you're given all those values for the bounds up front. And you want the sum of all the absolute differences of the pairs to be maximized. Yeah, I'm sorry, I was checking if it was maximized or minimized, but you want it to be maximized. So this one's kind of fun because it's DP, but it's also DP with like a small insight to do it correctly. So I think it'll be fun. And that's actually all the problems for the contest today. So I don't believe I have anything else to talk about, although if you have any questions for anything, whether they be like contest questions, MCP questions, interview questions, big life questions, feel free to throw them into the chat and I'll do my best to answer them. But until we get something like that, I think I'm just going to put on some music for you guys, and I will come back when we have some updates. Talk to you guys then. Hello, I am back temporarily because it looks like we've had some progress on the contest and we have a question in the chat. So first, let's talk quickly about some of the contest progress. So we've had, it looks like at least 3 people try out this first problem. And it looks like it's been harder than I intended. We've only had 1 full solve so far, but hopefully we'll see more of those. And somebody's already gone and solved bill division. It looks like, oh wow, sorry, all 3 people have gone on and solved bill division. It looks like that might have actually been easier. And it seems that everybody right now is probably still working on pairs. Now, I guess there's a bit of a difficulty jump between bill division and pairs, but it shouldn't be too bad. I'm confident that you guys can get this. Alright, now also, I see a really good question in the chat from Ran Sidiku. It asks, and sorry if I butchered your name, it asks, if your goal is to prep for interviews and get better at competitive programming, should you focus on one style of problems over the other? Ooh. So that's a very broad goal, to both get better at competitive programming and interviews. But I would say the most important type of problems to focus on, rather than being like a category of problems like DP problems or graph theory problems or something like that, I'd say the most important thing to focus on would be on problems that you yourself specifically couldn't solve before. So think about like if you wrote a contest or you just like chose some problems to solve and you found there's some you couldn't do, those are the ones you need to do, right? So like you get better by doing things that you couldn't do before. And if you can continually do things that you couldn't do before, then you'll be able to do like quite a few more things. I guess it sounds kind of silly, but I think like fundamentally that's like the approach. Beyond that, if you don't have too much experience, there are a few categories that just like show up a lot, so they're worth knowing, especially for interviews. Like, it's really important to know like the basics of graph theory. Like, you need to know enough graph theory to be able to run a depth first search or a breadth first search. Especially, companies often ask you to do a DFS or a BFS on a grid, so make sure you're able to do that. Beyond that, it's good to know some simple DP. So particularly, there's a DP problem called coin change on HackerRank. You should know enough DP to be able to solve that problem. And you can also just look up, I don't know. So it depends on what company you're applying for, but you can normally look up like common questions they ask. So I know, for example, like lots of McMaster students will apply to Microsoft, and Microsoft is actually like a pretty standard repertoire of questions. For instance, without fail, Microsoft nearly always asks you to reverse a linked list, which is like super classic problem. So it can be really good to look up on like a company-specific basis, like the sort of questions they ask. And for competitive programming, it's a bit more general because there's more topics. I'd say for competitive programming, a good way to to improve or to figure out what problems you need to work on is try out a Codeforces contest or two. So write like a Codeforces like Div2 contest or a Div3 contest. You'll be able to solve probably like some questions, but there'll be like a lot of questions you won't be able to solve, and that'll tell you the sort of things you need to focus on. Like ideally, what you should do, I'll even pull this up for fun, is you should. Oh god, I can't spell. Wait. Ideally, you should go into Codeforces, and you should find a Div3 contest. So if you go to contest, you will see, let me wait for this to load. Yeah, we've got, oh, there's no Div3s coming out. You can still do it. A Div2 still works as well. It's not as good. So you can rate, they have these Div3 contests, and they're like, they have a lot of questions, and they're really good if you don't have that much experience. Even if you do have a lot of experience, it's still good. Like, I still learn a lot like writing them. But these would be really good to figure out what you need to know. And Div2s don't hurt either. There's actually a Div2 coming up this Sunday, which will be fun. Cool. So I hope you all enjoyed my update. Let's see, do we have any other update? Do you have any questions in chat before I go back off again? Okay. Yeah, I don't think we have any more questions. I'll give you guys some music again, but if you guys have any more questions, I love answering questions like this, so just chuck them into chat. I'll do my best to answer them. Hello. It's about time I gave another update. So, it looks like, as I refresh the page right now, that most people are still stuck on pairs. I hope I hope it isn't too difficult. It's a little tricky. You need a special insight, but I will say it looks like at least like everyone is getting like quite a few partial points, which is really good. If you're stuck on this, like it's totally okay to move on to like other questions and come back. Like I think you'll enjoy the next problem quite a bit. So it could be good to like do that and go back to pairs. Now I see we have another question in the chat, again from Ryan Sidiku, and it says leak code or cracking the coding interview for interview prep. Like what's better? What should I do? So as someone who's done both, so for context, I think when I was back in second year and first applying for jobs, I got the on-site from Microsoft, and I was like, oh gosh, I have to actually prep for this somehow. Like, what am I going to do? And I think I purchased a copy of Cracking the Coding Interview at that time. And I'd say it's pretty decent. Like it goes through like most of the topics, like the basic topics you need to know. It doesn't go through like very advanced things or anything, but it certainly goes through enough to get you like an entry-level internship, like for sure. And I guess it can be better than leak code in the sense that leak code can be quite a bit more undirected. Like it's a bit, you can feel a bit uncertain as to like what particular thing you should work on. Whereas cracking the coding interview is quite a bit more guided in that it'll point you towards specific things. So if you have the time to do both, what I'd recommend is to start with cracking the coding interview. Like just work through the content. It's a big book, but there's not that much actual content in it. So it's very doable to like work through it all. And then if you have time, like after doing that, then it could be good to do like actual leak code problems. So I guess, yeah, the perfect plan then, going off what we said earlier, is something to the effect of like work through cracking the coding interview, perhaps do some like leak code questions like specific to the company you're applying for, if you can find those. And failing that, just like do like leak code questions in general and get a good sense for it. And like, I guess if your target is like specifically interview prep, if your target is specifically competitive programming, I'd say maybe I don't know, maybe less leak code. I find leak code is a lot less enjoyable. Like, so if you're doing competitive programming, I assume you're mostly doing it like for the enjoyment of it itself. In which case, I find like I don't know, leak code can get a bit like onerous, versus like code forces or something like stays kind of like new and exciting as you look at new questions. So if you're doing competitive programming, I'd focus on more doing like code forces, maybe at Coder. You can look that up. That's another good site. Or just even like ICPC, past ICPC contests. Although I will say for past ICPC contests, they're kind of long. Like they normally have 10 questions. So they're way better if you can do them with friends. So like I'd like message a friend and say like, hey, we should do this ICPC. Now this relies on you having friends that want to do competitive programming, which may not be the easiest thing, but worst case you can introduce your friends to competitive programming. So I think it's a win-win. Cool. So it looks like everyone's still working on pairs then. For anyone who's like doesn't understand why the solution is TLEing for this, notice that the input, like your n here in the input is 10 to the 5, which is really quite large, which means an n squared algorithm won't pass. So you're gonna have to do something that's linear or like basically linear if you want to pass this question with like full points. That's like my one hint. So and then I guess maybe I'll give a second hint too. Hashing might be like super useful towards achieving this goal. For instance, if you've ever heard of the problem two-sum, that was the hint I was going to talk about earlier. If you've heard of the problem two-sum, this is very similar to that in spirit. Okay, and with that, I'll disappear once more and bring you back some tunes. All right, time for another quick update. So looking at the contest now, I was very happy to see that somebody has solved 3D surface area. I think this is really quite a fun problem, since it's very visual. I'm really fond of visual problems, which is, I guess, one reason why I really like geometry problems. Because I don't know. Normally, all the intuition and insight are very visual as well. And it seems the person who solved it is QWERTY MDU. Congrats to you, QWERTY MDU. Oh, it's Jake Do. Oh my god, this guy's a previous winner, I believe. Good on you, Jake. All right, and then as well, I noticed that we had another question in the chat. This one is also from Ryan Sidiku. He asks, how do you feel about your last year of school being all online? I'd have to say I probably have mixed feelings. On one hand, actually, sorry, I'll do like the generic one first. So on one hand, like it does feel sort of bad. Like you're paying like thousands and thousands of dollars to attend like some online school, and that's probably like the same, if not worse, than like if you were to just do like MIT OpenCourseWare or something, right? But again, it still gets you a degree, I guess. But on the good side of things, it's been like pretty convenient, which is nice. Like sorry, like for example, I guess you don't have to commute to classes or anything. Since your lectures are recorded, it makes it easier to review. And like for classes that aren't as useful, you can watch them at like 1.5x or 2x speed and burn through them like rather quickly, which is nice. Although it is like, I don't know if our graduation is going to be online as well. I assume it's going to be. That's sort of like disappointing. And I guess, yeah, like half the reason to go to university, right, is just like the social aspect as well, right? Which clearly becomes like quite a bit harder when you can't interact with people in person. So all in all, mixed bag. I'd rather be in person, but it's not like the end of the world that it's online, I guess. Yeah, that would be my summary. Super quick summary. Let's also take a look on the leaderboard over here. Okay, interesting. So Jake Do has jumped to the front by solving that 3D surface area problem. Be interesting to see how this changes in, I guess, for the rest of the contest. At this point, we have, I believe, just is it under an hour? No, sorry, just over an hour left. So in this last like hour and 10 minutes, it'll be interesting to see what people solve. I think people could definitely solve cut the tree. I think it's very doable. If you can do a DFS, I think you can do cut the tree. I'll say that. So I wish everybody luck who's trying that out.
noticed the lights were on, and I thought you might be home. I wasn't sure.
Alrighty, we are down to the last 30 minutes of the contest. And I'm going to do my usual updates. So, it looks like you've been stuck for a little while. Paris ended up being much harder than I thought it would be, which is interesting. But I'm still curious to see if anybody solves cut the tree, although it does require some graph theory knowledge. And it's another thing too. I find it's really easy to sort of give up in the last hour or last half hour of a contest. But I find it's good if you can stick with it. I don't know. I feel like it benefits you. It's really easy just to say last half an hour, no need to keep going. But if you can stick with it, stick right to the end. I feel like it helps you grow. And now we've got another question from Ryan Sidiku. He asks, "What is the meaning of life? What is the meaning of life?" That's I feel like these questions have escalated in difficulty. So I err on the side of being a bit nihilistic, I guess. So I'd say I don't know if there is a nice, good, overarching meaning of life I could give you. But I'm sure if there is one, then it must involve ICPC World Finals. I'm sure that's got to work in there somewhere. But I think that's about all I can give you. I guess so. But for anyone who's still in the contest, I'm going to give a few hints for the problems that people are stuck on, just to keep things moving. So for pairs, as I mentioned, this problem is really quite similar to two-sum, and we notice that n is about 10 to the 5. So a few insights we can make for you guys are notice that you're going to need linear runtime, really, or maybe n log n you could get away with, but I don't know a good n log n solution for this. So maybe around linear runtime, and you need a technique that's somewhat like what you'd use for two-sum. So using hashing or something like that for this could be very beneficial. I guess the difficulty would be figuring out what you need to hash here. For cut the tree, this isn't too bad. So consider you only cut one edge, right? So we only cut one edge, and you could, if you think about it, it is possible and not that bad to make a DFS that would return the sum of everything in its subtree. And if I know the sum of everything in the subtree, and I know the sum of everything in the total tree, I should know the sum of everything not in the subtree. And so by looking at comparing the sum of the subtree to everything not in the subtree for every single subtree, after calling DFS from some node, that should be all I have to do really. It could be one of those would be the answer, right? So you literally just have to look through those without spoiling too much. So that's the hint for there. And then this last one, I don't think I can give that much away for it. I can say a lot, but it won't help if you're not too familiar with DP. So this is effectively for this, consider n is 10 to the 5. So once again, we need effectively a linear algorithm or something close to that. So for this, we can actually do a linear time DP. I did a 2 by n DP, if that helps you. But I won't spoil any more than that, because without doing more than that would literally just explain the solution. But this one will be really fun to go through later at the end of the contest. And with that, I think that's all I had to say. Ryan Siddiqui, I hope you end up finding a nice meaning of life. Do tell me if you find a particularly nice one. And I'm going to bring back the music. All right, we are down to the last few seconds of the contest. And once that has wrapped up, I'll be announcing the winner. And we'll begin our upsolving. So, let's see. I believe the contest is actually just ended. Awesome. So if we look at the leaderboard, we will see in first place we had QWERTY MDU, followed by Chuck20, followed by Black Cobra coming in third. Thanks to everybody for competing. And I guess I already mentioned this at the start, but this is the last contest we're having in this format, so it was nice to see everybody come and give it a try. And I hope you enjoy our new formats in the weeks to come. And now with that out of the way, it's time to do some upsolving. So our first problem was a problem called breaking the records. Now in this problem, the idea is we're given an array of integers which are scores that I think it's someone has scored playing college basketball. And the idea is that we want to look through these scores from left to right, and whenever we get a new maximum or a new minimum, we want to increment a counter corresponding to that. So that's to say I'll have one thing that counts how many new minimums I've got, and one thing that counts how many new maximums I've got, and I'll increment them whenever I see one of those. So this shouldn't be too bad to code. What we'll do is first I'm going to go to Python 3. So let's do that. Delete any of their existing code. I think you're generally better off pretty much always deleting the existing code. All right. So first we're going to take input. We see the input is 2 lines. The first line contains n, which is the number of elements. The next line contains an array with that number of elements. So we'll read in n, and we'll read in a. So this one line here looks kind of terrifying, but this is a really handy line for reading in a list of input in Python. I actually go over it in we had our essentials workshop. I review why this line actually works because there's a lot going on here. But you should definitely take the time to piece apart why this line works. But anyways, now that we have that, let's keep track of the min and the max. So what I'll do for that, I'll make 2 variables, min and max. And to start, I'll just set them both equal to a and 0. Then what I'll do is I'll look through everything in A, and whenever I get a new minimum or a new maximum, I'll increment a counter corresponding to that. So let's make counter 1 and counter 2, set them both to 0, and let's say if my current element is, let's see, what order do they want? They want max to min, right? Let's see. Yes, they want us to print out how many times we got a new max, followed by how many times we got a new min. So I'll do this part in that same order too, just for fun. So I'll do if my element is bigger than my existing max, then max equals this element, and counter 1 plus equals 1. Otherwise, if my element is less than my min so far, then min equals my element, and counter 2 plus equals 1. Then we just print our counter 1, counter 2. If you use a comma in the print statement in Python, it'll just add a space between these 2 values, which is a handy thing to use. So let's try that. All right, we pass the samples, and we can submit. And we have passed the full test cases. Nice. Okay, cool. That brings us to question 2. For whatever reason, people actually had an easier time with question 2 than question 1. All right, so the idea here is that 2 people, Anne and Brian, are going to some restaurant, and they order some number of items, and the price of all these items is given to us in an array called bill. So for example, up here, we see that bill equals 2, 4, 6. So that means the items had prices of 2, 4, and 6, respectively. Now, how this problem works is Anne and Bill eat everything together, except Anne doesn't eat one of the items. And specifically, she doesn't eat the item with index k. So k will be some index from 0 to n-1, and we say that Anne doesn't eat that item. So then, knowing that, if we were to split this bill fairly, the amount that Anne should pay should be the price of everything she ate. So that's the price of everything minus that one item divided by 2. but we're also given the amount that Anna actually paid, which might be like more than this. So what they want us to do is they want us to calculate the amount that Anna was charged, which is like this thing right here that's given to us, this B value, minus the actual amount she should be paying, which is the sum of everything minus the one thing she didn't pay divided by 2. So we can just do that because that's just math. So the only other thing we might have trouble with this in this problem is input's a bit weird, and we need to remember to print bon appetit if this difference is 0. So first, let's take a look at the input format. We see that its first line has 2 integers n and k, followed by bill, followed by b. So let's read those in. So we'll go nk. I'll zoom in a bit too. Okay. Cool. We've got bill. And we've got b. So now our final answer, we said, would be the amount she was charged, which is given to us as b, minus the amount she should have been charged, which is, let's see, be the sum of everything in bill minus bill at k, which is the one she didn't eat. I have to make sure to use parentheses here. It'll be all that divided by 2. Let's try that. Wrong answer. Why? Oh, yeah, sorry. So we get this difference, but if this difference is 0, we're supposed to print bon appetit. So let's just put an if statement to check for that. There we go, sorry. So if this difference is 0, we should print, and I can't spell that, so let's copy paste that. Bon appetit. There we go. Otherwise, we actually just output the difference. Cool, that passes the samples. And if we submit that, cool, well, we solved everything. Nice. So now we're going to move on to the third problem, which is pairs. So as I mentioned during the contest, this is very similar to something called twosum. So the idea here is we're given an array of integers, and we want to figure out how many pairs of these integers have a difference equal to like the sum value k that we're given. And also note, where does it say this? Yeah. Oh wait, maybe not. Sorry, I was gonna say that all the elements are unique, but I'm actually not sure if that's true. Yeah, no, I don't see that. Okay, I guess we can't assume they're unique then. Okay. So how I'd like to go about this is we can think, so what has to be true? Let's think, what has to be true for there to exist a pair of integers that have a difference of k? So for that to be true, we need to have 2 integers a, b, such that, and I'm choosing a, b, I'm saying a, b arbitrarily. I could call them food bar if I wanted to. But we need 2 integers a, b such that a minus b equals k. So then what we can think about doing is, this is equivalent to saying we have, how do I do this? I do like b equals a minus k. That's equivalent to having this. So for a given b, that's like saying for like a given integer like b, I should be able to find another integer a. Sorry, I should be able to find another integer that's equal to like a minus k. Oh, what am I even saying? Wait. Yeah, sorry. So sorry, if I choose some a, I should be able to find another b such that b is equal to a minus k. And for any instance of this, I get one value in my answer. So what we can do then, oh, sorry, yeah, look at this. So they are guaranteed to be unique. That makes our life easier. So what we can do then is we can effectively try every a, so every possible a, which can be every element, and for that every possible a, look for look for like corresponding a minus k's, which give us values. So this will make a lot more sense with an example. Pretend we had like, let's say we had the elements, like, I'll choose some random ones. Sure, 1, 4, 2, 7, and 8. And let's say we're looking for a difference of 6, so that'd be like k equals 6. Then let's look at what element would need to exist for us to find a pair. So if I was looking at 8, like I can make 8 my a, and then a minus k would become 2. So that means that if I'm looking at 8, if there's also a 2 in here, that means I get one value from that because I can make the pair like 8, 2. Now, note I only subtract k, I don't add k, because I don't want to double count like 8, 2, and 2 minus k. So I only check like looking down, so to speak. Like I check, like I put 8 as my a value, and then I look down to something like 2. Now, similarly, like if I look at like 7, I can say, all right, what's like 7 minus 6? Well, 7 minus 6 is 1. Do I have 1 in my array? Yes, so I can make that. And then I can go maybe like 4, let's say. Maybe I take a look at 4. And I look at 4. I say, well, do I have 4 minus 6 is negative 2. Do I have a negative 2? No. So I don't have something with this difference. So with that in mind, let's try actually coding this up. So our input is nk on the first line and the array on the second line. So let's read that in like usual. There we go. Okay. Now I'm going to do something. Oh, wait, did I? Okay, wait, I'm missing one parenthesis. Okay, sorry. So I'm going to do something a bit different. I'm going to take my array now and cast it to a set. So a set in Python is like a set in math. So what it does is it stores like a collection of elements without any particular order. And a cool thing about sets in Python is they can actually tell you in constant time if an item is in them. So, for instance, let me double check and make sure you guys can see this. If I pull this up here, okay, beautiful, you guys can see that. Make my font size a bit bigger. Oh, by the way, this is like Windows subsystem for Linux, which is like super handy. Highly recommend. So let me shrink this a bit. Okay. So this is Python 3. So if I make a set in Python, I can go like, I'm making a set. It's going to contain like 1, 2, and 3. We can view our set. What Python does is it lets us check if an element's in that set by doing things like, I can go like 2 in S. And this is true because 2 is in my set. But I can do something like 7 in S and say, oh, this is false because it's not in my set. But what makes Python really cool is that this operation actually takes constant time. So that means that even if I was working with like 10 to the 5 elements, like what I have in this question, I can still tell in constant time if I have an item. So then what I can do here is I can iterate through all the items in my array. Oh, sorry, I'm also going to make a counter just to store my final answer in. But I can iterate through all the items in my array. And if e minus k is in my set, and now note this check here takes constant time, since sets in Python can do membership in constant time. So if I have the smaller element, that means I have like that a minus k value I was looking for, which means I have a pair with a difference of k. And so then I'd add 1 to my answer. And then I just print the result. And so let's think about the runtime of this too. So consider this loop goes through every element. So there's n elements, so that's like linear time. And then inside of my loop here, I do like constant time. So my overall runtime is also just like linear then, which is really, really nice. And let's see if this actually works though. Cool, so this does seem to work. We'll try submitting it. And it looks like we passed everything. So it's not too bad. It's very similar to 2-sum. So if you want to try a similar problem, now that you know how to solve this, definitely try solving 2-sum. Okay, I absolutely love this problem. So this problem, you're given this weird sort of like 3D shape. And the idea here with this 3D shape is that we have a grid with H rows and W columns. And that grid sort of composes the shape. And we're given this array, A at ij, and A at ij is the height of some like particular spot in the grid. And what we need to do is find the surface area of the shape. So there's a few insights to make first here. So first, notice that the surface area of the top and the bottom of the shape are really easy to compute. So the surface area of the bottom, we can see, is just a square. It's h times w. But if you think about it, if you imagine looking at this from a bird's eye view, the surface area of the top is also h times w. So we can get the surface area of the top plus the bottom by just going 2 times h times w. So then all we're left with are these weird side pieces. But the insight here for these side pieces is that consider like any two of these adjacent pieces. We'll notice the amount of surface area we get from those two adjacent pieces is like the difference in their heights. So like here we have a difference in the height of 1, and you'll see we've got 1 area here, versus here we made a difference of height of 2, and we got 2 area, and so on. And then we also have to do that for the sides. So the sneakiest way to do this for the sides is just to buffer our array with with zeros along the outside, and then we will just compare like the difference in height between this and like 0. So let's try coding that. So the input format is we're given height, width, and then the array, the 2D array, A at ij. So let's read those in. So we'll go, instead of height, width, I normally read it in as nm, just because those are more standard. So let's do that first. Nm equals map into input.split. Next, we read in the array. I normally read it line by line, so I start with an empty list, and then I go, for n times, I want to read in the line and append it. So let's append list map int input.split. So that reads in. So this here reads in one line like this, and then we append that line to a big list. So we end up with a list of lists where we're basically just storing a list of the rows. So it's just like a regular 2D matrix. Now, actually, I was going to do this, but now I think I'm going to actually do something more fun. Should I? Yeah, actually, I will do it this way. I will do it. So originally, I was going to zero buffer it. I could zero buffer it. You know what? I've never solved this with zero buffer. Let's actually do this with zero buffering. It'll be fun. So when I say zero buffering, what I mean is pretend, for example, I'll do like a simple example. Pretend, I'll do okay, wait. So pretend our thing was like 1, 2, 3, 4. So those are our heights. That's our height matrix. So I'd have to compare the heights inside this thing. Like I'd have to compare 1 to 2 and 3 to 4 and 1 to 3 and 2 to 4. But then I'd also have to add in, effectively, like I'd have to add in 1 plus 2 plus 4 plus 3 to get all. Actually, no, even I have to do that multiple times even. Sorry, because I'd have to. Sorry, if you imagine this is the shape, like there's the 1 square above this 1, and there's the 1 square to the left of this 1. Somewhere there's like the 2 square above this 2, and the 2 square to the right of this 2, and we have to account for all that surface area. So one sneaky way of getting around that and not needing special code for it is just to surround the shape we're given in like I don't know what to call it, a wall of zeros. And so we can just do comparisons with 0. So let's try doing it this way. It'll be fun. So if I want to do this, then I need, before I start putting anything on, I need zeros. So let's go to start, a.append 0 times, let's see, m plus 2. Now you ask why m plus 2? It's because our width is m, and if I add a 0 on each end, that'll bring us up to m plus 2. Next, instead of appending just this as we have it right now, I have to add a 0 onto the front and a 0 onto the end to get that buffering. Okay, so I'll do that. And I'll still just append that like normal. I could have done this on 1 line still, but I want to make it a bit more readable. So 2 lines. And now let's append on our bottom row of zeros. Cool. So now we've surrounded this thing in zeros. So now the rest of the problem really isn't too bad. All we need to do is add on the surface area at the top, the bottom, and all the internal differences in the matrix. So when I say internal difference, I mean like a difference in heights between two things like horizontally, or a difference in heights between two things vertically. So let's do that. So our results let's make a result variable. We'll initialize it to 2 times n times m. Then I can, first I'll iterate and I'll check all the horizontal spots, then I'll iterate and check all the vertical spots. So let's do horizontal first. So I'll look through every row. I'll look through every column except the last one. Now the reasoning for that is I'm looking through something of width 2. So I want to iterate on every spot except the last spot, because if I'm looking at something with width 2 and I go on the last spot, my second item would be out of bounds. And now what I'm going to do here is add to res the difference in height. So 8ij, let's do, 8ij plus 1 minus 8ij. And we just take the absolute difference in heights here. Since you think like, back to this diagram, if we have like an increase in heights or a decrease in heights, we still just add the difference to our surface area. It's the same either way. So let's do that. Okay, and I need to do the same thing for the vertical portions. So for that, I'll go for I, and this is the same thing, but effectively just flipping rows and columns. So for I in range m minus 1, for j in range m, res plus equals absolute difference of array at I plus 1 at j minus array at I at j. Then we just print our results. Let's try that out. Oh, and I got this wrong. All right, let's figure out why I got this wrong. Okay. So here I have a 1x1 matrix. Oh, I know why. Okay. So this is a really good insight. So here, notice I have a 1x1 thing, but really I should be working with if I have a 1x1 thing, like here the input's effectively just like 1, right? But I add 0, so I effectively instead work with this. So really then I have a 3x3 thing. So I should add 2 to my n and add 2 to my m. So let's actually do literally that. So let's go n plus equals 2, m plus equals 2. Now you'll notice I was very careful to put this after this line here, because like this I only want to add like the top and bottom of the actual thing, not the top and bottom of my like sketchy extra 0 part. So I add the top and bottom of the actual thing, I increase my n and m to include the 0 part, and that makes it so I'll iterate through everything. And now let's actually see if we get the right answer, looking at the differences here, and it seems like we do. Let's submit this guy. And all moment of truth, it's not showing us our points. There you go. It seems like we've solved all of them. That's good. All right, next, I really love this problem. So actually, I'm even gonna pull up the thing I wanted to talk about earlier. So the problem, so I encountered something very similar to this problem on a previous ICPC once. It used this as a subproblem, but I was unable to like figure this out at the time. So let me find this. I believe I don't know if it's 2017 or 2016. I should remember it was question F. Is it this one? It is this one. Okay, cool. So that worked out. So I'm gonna send this problem in the chat because it's a good problem. Highly recommend you try this. I'll post this guy. But this problem effectively uses, like, the key idea here is the same as the key idea here, which I hadn't seen. So here, sorry, I should actually explain the problem too. Here, the idea is we're given some tree where each node has a weight associated with it, and we want to cut one edge in this tree, which will leave us with 2 trees, and we want to minimize the difference in like the sum of all the nodes in each tree. So the best answer here, for example, is I cut this edge 2, and then I'll be left with the nodes nodes with values 1, 2, and 6 in this tree up here, which have value, let's see, 9, and the nodes 3, 4, and 5 down here, which have value 12. Those have a difference of 3, and it seems that 3 is the smallest absolute difference I can get if I try everything. So this problem actually isn't too bad, because all we have to do here is we're going to run a depth first search. We're going to iterate through every node. Actually, I want to draw this out too, because this is weird to think about if you haven't thought much about graph theory before, but it's really intuitive once you see it. So I'm going to pull up a Jamboard right here. For reference, Jamboard is like some drawing thing that's useful when I do these live streams, because I can, I guess, like draw out the test cases and whatnot. So I draw my Jamboard, open this guy up. Okay, there we go. And so I kind of prefer to view this like, instead of, they've kind of shown us this tree horizontally, I like to draw it like top down. So let's say we draw it like this. So let's see, under 2, I've got a node 6. Under 3, I've got nodes 4 and 5. Okay, so consider we have this tree, and we're to make a cut somewhere. And what happens when we make a cut? Like, let's say I choose to make my cut like right here. When I make that cut right there, what ends up happening is I separate off like this tree here from the rest of the graph. Like, for example, I'll do another cut. Another cut I could do would be right here. If I cut right here, then I'm effectively separating off this tree from the rest of the graph. And what the problem asks us to do is asks us to take the sum of everything in here, so I'll draw a little sum symbol, and the sum of everything in here, and we want to minimize the difference between these two sums. So insight number 1 for this, I guess, is consider, let's say we run a DFS. So DFS is called a depth first search. And how it works is you start it on some node, like I'm going to start on this root node right here. And technically, it doesn't actually matter what node I can start on. I can start on like any node and it would still work. But I'm gonna root this node, this tree at the first node, and call my DFS here. And what my DFS will do, or what DFS does in general, I guess, is that DFS calls itself on all the children recursively. So by chance, like DFS might go to 2 first, let's say. So we'll call DFS on 2. Now I'm looking at 2, which will then call DFS on its child, which will look at 6. And so consider that DFS in this manner will end up looking at every node in this tree. And what we could do when we're looking at every node, which I think is an interesting thing to do, is to look at all the nodes in the subtree rooted at that node. So what do I mean by that? I mean that, let's say we're looking at this 6. I'll say that all the nodes in the subtree of this tree rooted at 6 are any nodes that are like further down the tree than 6, of which there are none. So that means our subtree start like rooted at 6 includes only 6. So if we were to store all the sum of all the things in the subtree, that would give us a value of 6. Like similarly, if I want to store the value of all the things in the subtree at 2, that would be 2 and 6. The sum of 2 and 6 is 8. So I may associate the value 8 with this. Now the next thing to consider is I want to, so I now know for a given subtree what the sum of that subtree is. And I know I'm left with like this subtree, like for example, you can imagine this one, I'm left with this subtree, and I'm left also with these like this other stuff. So we found out we can actually compute the sums of the subtree really easily by just calling DFS and like summing on the way up, which is like pretty easy. However, what's much harder, or I guess not what's much harder intuitively, I guess, is figuring out the sum of everything remaining. But there's actually a really easy trick to this, and that is consider that the sum of everything remaining, so this part that I'm going to draw on like, I don't know, I'll go draw on green. The sum of this region right here is really the sum of everything minus the sum of the subtree we care about. So what we can do then, I mean, we pretty much figured out this whole question. We can run a DFS, and then during our DFS, we're going to get the sums of like whatever subtree we're looking at. And the sum of everything not in our subtree is going to be equal to the sum of everything, I'll just say like sum of all, minus sum of the subtree. And so the sum of the subtree we get from computing our DFS as we go along, and the sum of everything we can just pre-compute. And then consider that when we look at a particular subtree, we're effectively considering chopping off the edge right on top of it. Like for example, if I was considering this subtree, then the subtree I'm left with is this other, sorry, the other tree I'm left with is this guy up here, which means that it's as if I cut this edge. So by considering every node, I'll actually end up considering cutting every edge. So if I just do this comparison for every single subtree, I should find the optimal answer then. So then our implementation actually becomes pretty clean, so long as we read the input format. Let's see. So the input format is, yeah, so we get n, which is the number of nodes. Then we get n values on the next line, which are the weights of each node. And this is followed by n minus 1 edges. So there's a property trees have. A tree with n nodes will always have n minus 1 edges, which is why we're given n minus 1 edges here. So let's go. And we'll say we read an n. Let's read in our weights. I'll call this w. Like this. Now I have to read in our graph. My favorite way to store a graph in Python is to use something called a default dictionary. All the default dictionary does is, so let's read a regular dictionary. Actually, I've been shown this. This is really easy to show. So let me open up my Python again. So if you have a regular dictionary in Python, a dictionary is a mapping between key and value. So I could say something like, I don't want to call it A. Let's call my dictionary D for dictionary, just for fun. Okay. So if I say dictionary at blue equals moose, I'm just doing random values. Then what my dictionary stores is a mapping between the string blue and the string moose. So I can go, for example, D and blue, and my dictionary will tell you, well, the mapped value there is moose. And so another common thing I'll use dictionaries for very commonly is things like counters. So I might let's say I'm counting the frequency of letters. I might say like D at A equals 0, and then whenever I see an A, I might go D at A plus equals 1. Maybe then I see a B, so I go like D at B equals 0, D at B plus equals 1. And if I see like another B, maybe I'll go D at B plus equals 1 again, and so on. And then eventually, I guess ignoring this moose thing, I'll even delete it. There we go. So ignoring that thing, we can use a dictionary to keep track of things like frequencies. Now, this can often make our code really gross, because we end up needing to do things like, notice how I've got like these two separate lines here. So it's like, if I'm adding a key to my dictionary, I need to explicitly add it by assigning it to something. But if it already is in my dictionary and I'm like making a counter or something, I can just increment it. So I have to have like an if statement for that, which is really gross. So instead of doing an if statement for that, we can use this thing called a default dictionary. So if we go from collections, import default dict, then I could go, let's say like f equals a default dictionary, and I'll set this to int. Now what this will do is I can use this as a frequency counter, and I can say things like f at a plus equals 1. And you'll notice I never added a to my dictionary, but you'll see here now I have it associated with 1. And how that's possible is with a default dictionary, if you try and access an element that's not already inside of it, it just initializes a new element to like 0. So what happens here is like I try and increment f at a. My dictionary says, oh, a is not in the dictionary. So it adds it to the dictionary, sets it to 0, and then it increments it. So I use this to store graphs. So when we store a graph, we normally use something called the adjacency list representation. So what we want to store effectively is, I'll even like scroll over so you can see this graph here. What we want to store, what's a good graph? Sure, let's draw this. So what we want to store is edges in our graph. So see here, like for example, I have an edge between vertex 1 and vertex 2. So I might have like some graph data structure as like a dictionary, and say that like all the edges out of 1 are like 2, or like all the edges out of 2 are what? 1, 3, and 5. So the idea here with this adjacency list representation of a graph is that if I access my adjacency list at a given node, it'll tell me all the nodes that are adjacent to that node. And this is really useful when we implement depth first search, because it lets us see all our neighbors. So here we run into a similar problem that we had with frequency counters, where if I don't already have, so like if I'm adding a bunch of edges and I don't already have like I don't already have a node in my graph, then I have to do like graph at like my node equals like a new list, like an empty list, and then I can append to it. So instead what we can do is we can make a default dict of list. And then if I want to add an edge, like let's say I want to add an edge from 1 to 2. Oh, sorry, I have to, let's call this G. If I want to add an edge from 1 to 2 now, I can just go G at 1 dot append 2. I don't need any other fancy logic. And it makes this mapping from 1 to 2, which is super handy. So then you'll see that we do that here. So here, and you'll see I abbreviate default dict to DD, just so it's easier to write. But I can make a graph that's default dict of list. And this means that if we look up a key in our dictionary and it's not there, it'll just make that, it'll add that key and set it to an empty list, which is really handy. So now I can iterate through all the edges. And I'll read in the values for each edge. And now this part's really easy since we have a default dict. I can just go G at U dot append V and G at V dot append U. So with this graph representation, you can think of this as saying, so G at U is the list of all the neighbors of U. So add to that list of neighbors the node V. And similarly, in V's list of neighbors, add the node U. So they both like see each other in their list of neighbors. So we call this like a bidirectional edge, or like, I guess, yeah. So, oh god, I wasn't planning on talking about this, but you can normally think about graphs as being directed or undirected. So when you have an undirected graph like this, you can like kind of think of that as having edges that go like both ways. All right, so now we've written our graph, and we want to do a DFS. Oh, sorry. Before we do DFS, we should figure out the sum of all the weights. So remember, we wanted to figure out at every node what the sum of everything was minus the sum of the subtree. So first thing we have to compute is the sum of everything, which we can do beforehand. So let's call that, I don't know, sum all. It doesn't really matter what we call it. But I'll say it's the sum of all the weights. So that's pretty easy. We're done that. Next. I want to make a DFS that computes the sum of the subtree. So there's a bit of a handy trick here. So you see, I want to make my DFS take in 2 arguments. I'll call them x and parent. So x will be my current node, and parent will be the node I came from. So the idea here is that when I first call DFS, like let's say I call DFS on my starting node, I'll end up going to the left or the right. So let's say I go to the left. Now when I'm on this node to the left, I want to be able to visit my children, but I don't want to accidentally go and visit my parent again, because then I could like visit my parent and visit myself and visit my parent, and I could end up going back and forth forever, which would be really bad. So instead what I do is when I visit one of my children, I store the node I came from as a parent. So like if I visit 3, I'd store 1 as my parent. And then when 3 looks at its neighbors, it makes sure to ignore the parent so it doesn't go back to it. So what that actually looks like is in our DFS, we want to look at all of our children. So I'll go for like child in my graph at me, and I'll say if child isn't equal to parent. So I want to ignore the parent because I don't want to go back to that. And then let's see, we have to think about what the purpose of our DFS was. So the purpose of our DFS was to sum up everything for a given subtree and to compare that with like some global best. So I guess that means we need a few things. First, I need some global best. I'm going to store my best answer so far. And since we're trying to minimize this, I'll set it to some arbitrary large integer first. And if I want to access it in DFS, I need to call global. So I'll go global best. This just puts this best in the namespace here so we can use it. Next, I said we needed the sum of the subtree. So let's store that in a variable called sum. So for sm for sum, I'll initialize it to weighted x, so the value of this current node. And then what I'm doing in this part here is I'm iterating through all my children and adding the weight of their subtrees. So this is actually really cool intuitively. The idea is how I calculate the weight of a given subtree, like this guy right here, is to add its value plus the weight of all its subtrees. Sorry, to add its value, I would say its value plus the weight of all its children's subtrees will give us its value. That's cool. So here I'll just go like this, the value of my subtree is equal to value of myself plus the value of all my children's subtrees, which we could compute like this. Now, notice how we set our current node to be the parent so that our children won't come back to us. And then finally, we have to compare this against our best. So we'll say best equals the minimum of best. And let's see, the absolute difference between the total sum. Oh, actually, I did this kind of wrong. Sorry. Yeah, sorry, I did this very wrong. So when we're looking at a particular subtree here, like let's say I figured out the particular value of my subtree is like sum, right? Then the value of everything else, right, is going to be the value of, let's say I called it sum all. So I'll say sum all, and that'll be minus sum will give me the value of this. So I actually care about the difference between these values. I want to minimize this absolute difference. So that's the exact same thing I'm going to do here then. So I'm going to do absolute difference of sum of everything minus me, which is like the sum of everything not in the subtree minus the sum of, minus like SM, which is the sum of everything that is in our subtree. And then after all this, I have to actually call DFS, otherwise it wouldn't run. So I'll just call it on 1, but it would work actually if we called it on any node. And our root doesn't really have a parent, so I can just put in any values here, like none works, -1 works. I normally use -1, just because that would work in C++ as well. And then finally, we should just print out our best. So let's give that a whirl. We can run this guy. Oh, syntax error. Let's see. These are normally pretty easy to spot, or so I say. So big tip. This is like a programming tip in general, especially in Python though. If you see an error like on the first thing on a line, what it normally is, it's normally that you forgot like a parenthesis or something on the line before. So here you'll see I forgot this right parenthesis. So let's run this again. Oh, wrong answer. Okay, why? So sum A. Oh yeah. So for some reason I did sum A. This should be sum all because it should match this. Oh, also, a fun like Python specific knowledge thing. You'll notice here we declared globals like best as a global, but I didn't declare sum all as a global. Now I could declare sum all as a global like this, but I technically don't need to. So Python's kind of sketchy in that if you declare an assignment like this and you don't declare it as a global, Python will interpret that as that you're trying to create a new variable with the same name. So it's going to make it as two separate things. But if you try and access something and you're not assigning to it, you're just accessing it, even if it's in like global scope, Python will be able to find it. So that's kind of like a quirk of Python that's good to watch out for. So in any case, let's try running with that. Okay, am I blind? Okay, wait, there we go. Here. Still does not pass. All right, what's our bug this time? Oh, okay. So you'll notice my whole idea with this DFS is that I wanted to like DFS at X to return like the sum of everything in the subtree at X. So that means I have to actually return the sum. And you see this is necessary because we add this sum. So we expect it to return the sum of that subtree. Oh, it's still wrong. Okay, why now? Okay. Oh, okay, also this is another good thing to point out. So we should notice they give us n nodes, but these nodes are one indexed. So what that means is that if we have 6 nodes, they're going to be labeled from 1 to 6. But notice that I stored my weights in an array, so I access them by indexing from 0 to 5. So I really have two options then. I can either change how I store these weights, so I store them from like 1 to 6, like similarly to how these nodes are indexed, or I could just like make my node 0 indexed, which is what I normally do. So to make my node 0 indexed, I just subtract 1 from them always. So I should do this. And with that, looks like we passed these samples. Let's see if we pass the actual thing. And moment of truth, drum roll. Oh yeah, this is really fun. So this is actually a great question for learning. We see we have a runtime error here, and you might be very perplexed as to why we have this runtime error. So the thing here, this is actually really good, really fun. So Python has Python 3 in particular. Python 2 has this too, but it's not as extreme. But in Python 3, there's a safety feature called a maximum recursion depth. So if you recurse to too deep a depth, Python will hit this maximum recursion depth and give you like an error. For example, let's say you're in Python, and this is good because if you make a silly mistake in Python, this can really help you. Let's say I make a function called f, and my function called f, let's say it calls f. So it's a very boring function. It just calls itself forever. So normally, if there was no max recursion depth that you call this would basically continue until like it died, until it ate up all your CPU resources. If I just try and call this, you'll see it hangs. But in Python 3, there we go. In Python 3, you'll see what instead happens is we get this recursion error, and it says, hey, you've hit the maximum recursion depth. So I believe I don't know if it's exactly 1,000 or around 1,000. I believe it's 1,000. Yeah, actually, look at this, 996 plus 4. Yeah, so it's 1,000. So if you recurse to a depth of 1,000 in Python 3, it'll say, hey, you've gone too deep. You can't go any farther. And it'll stop you. And this is good because it stops you from doing silly things like recursing forever. But it can be a bit annoying in competitive programming if you actually intend to recurse to a pretty deep depth. Like here, for example, we can have up to 10 to the 5 nodes. So in the worst case, if all these nodes were in like one straight line, we might have to recurse up to 10 to the 5. So luckily, this maximum recursion depth can actually be set in Python. So to set that, all we need to do, this is good to memorize, you go import sys, and we just go sys.set recursion limit. Oh, they even have it for me. Oh, nice. And we're going to set it to, I'll set it to 10 to the 5 plus 7. So you might ask, why are you doing 10 to the 5 plus 7 rather than just 10 to the 5? I feel like normally, whenever you have the chance, it's better to give yourself a little bit of slack and leeway. Just because, like, it really sucks to be having, like, an off by 1 error. Like, if you give yourself only exactly what you need, it's easy to mess up and give yourself, like 1 spot too few or something like that, and then you end up ruining yourself. So instead, you can give yourself, like, a little bit more, and it's like a little safety net, and it's not enough to hurt your runtime or anything, or hurt your memory usage. So with that in mind, let's try running this guy again. This should pass. Nice. And let's submit it. Okay, cool. And we got accepted on all the test cases. Okay, so that brings us to our final problem. Now, I really like this final problem, partially just because this final problem is a dynamic programming problem, and it is well known that I really love dynamic programming. If you are not too familiar with dynamic programming, but you'd like to fall in love with dynamic programming, as one does, I highly recommend this AtCoder educational DP contest. It has like 26 dynamic programming questions, and they start like really easy and get really ridiculously hard. I'll even post that in the chat. That's really handy. But the best way to learn DP is just like try a few questions, read a bit about it. All DP is, when you really boil it down, is it's solving a problem by breaking it down into smaller problems and storing the solutions to those subproblems in like a dictionary or like an array or something for later. That's all it really boils down to. So let's actually get to the problem now. So this problem is called Sherlock and Cost. And the idea in this problem is that you're given some array B and you're trying to build some array A. Now the constraint is that when you choose a particular value for A at I, it has to be bounded between 1 and B at I. So you're effectively, you're trying to make an array of size, like, what is it? I believe it's n, right? And for any one of those values, it's just like bounded just like this, between 1 and B at I, as I mentioned. And now the weird thing is you're trying to maximize this function right here. So the idea is you take the sum of every like pair of integers. So like I take the difference between like the first 2 things, the next 2 things, and so on and so on. Like, sorry, like if I had the array, do they have a good example here? Yeah, here we go. Pretend this was my array, and I actually did make all my values exactly this. So I made my A at I like 10, 1, 10, 1, 10. Then my differences would be 10 minus 1 plus 1 minus 10 plus 10 minus 1 plus 1 minus 10, where I take the absolute value at each step. So instead of like getting -9 here, for instance, I'd get like +9. And I want to maximize that value. So to solve this problem, what we need to do, first we have to make an insight to simplify it a bit, and then we should be able to solve it using just DP. So the first thing I kind of thought about with this problem was that, so if we're maximizing all the absolute differences, I think that the sort of best case for that is if we have like a very like zigzag array, like 5 an array that goes like from a low value to a high value to a low value to a high value and so on, then I get like a ton of value for all these like zigzag parts. I contrast that to if I had like, imagine if I was like low the entire time, for instance, I would get like barely any value because it would stay pretty much the same. So my differences would be like effectively like 0 or close to 0. So my guess then, the thing I wanted to check out is that I can always achieve an optimal answer where at every step I either try and like make my value as small as possible, so that's to say to make it 1, or to make it as big as possible, so that's to say to make it big at b at I. So I'm saying my answer will always be 1 or b at I for every spot in my array. And let's think about if that makes sense. So there's a few cases. So I think how we can kind of justify this to ourselves. Let's say we had like a given, let's say we have a given solution where we haven't chosen like a maximum or like minimum value. We've chosen like some value in the middle, like any arbitrary value in the middle. I want to show that we can always get an answer that's better or the same. So there's a few cases for this. So I'm going to draw the cases like this. So I'll draw here. Actually, yeah, this seems good. So I'll draw like, pretend this is our choice. This is the element before us, and this is the element after us. So let's draw a few of those. Let's see, how many cases are there? There will be, I'm going to ignore the cases where we're exactly even with the element beside us because that's so boring. I'll just draw whether above or below. Then there's not too many cases. That should be 4 cases then. So I'll draw out, let's draw out these 4 cases. So I have beneath me, above me, beneath me, beneath me. I have above me, and I have above me, beneath me. So I want to say that if our element we chose for some particular 8i is in the middle, and I'm representing that element we chose is this blue thing, we can always choose a better answer by choosing something not in the middle. And let's see if that's true. So in this first case here, I can always get something better or the same. So in this first case here, if we're able to choose a guess that was like way below, then instead of getting the value for just this region here, I'd get the value for going all the way to here plus all the way to here, which is larger. Or I can't draw it because it goes off the page, but similarly, if we could get a point above, I could get more value there. And if I couldn't get a point above, and I was still bounded in here, but I could still go higher, then I would just get the same value. So we can show that choosing a point, like trying to choose like b at I or 1, will always get us will always get us the same or a greater value for this case. Now, similarly for this case, right here in the top right, we can get a better answer by increasing. Similarly in this case in the bottom left, we can get a better answer by decreasing. Similarly in the case in this bottom right, it's like the same as our first case, where we can get a better answer maybe up here or maybe down here. Or I can answer this the same in here. Cool. So that's a really big insight. That tells us we can always get an optimal answer by always choosing at every spot either the biggest element or the smallest element. So the next bit's a little bit tricky. So to actually solve this, we need to come up with a DP to break this into like smaller problems. And so let's think. So DP, what you normally do in DP is you associate a state with like a value. So in this DP, since I have like up to 10 to the 5 elements, I'm going to think this is probably going to be like a linear DP. So I'm probably going to store something for every I. So I'm going to think like maybe I want like a DP at I sort of thing. And then I think, well, at I always have 2 choices, right? At a given I can either choose to go on the bottom or to go on the top, based like to be a 1 or to be b at I, based on our insight that we saw earlier. So maybe I can make a 2D DP called like I at C, where C is my choice. So this will be, I can make this like 0 or 1 or something, where it's like 0 if I choose to go and like choose 1 and go on the bottom, or I make like this value 1 if I choose to do like b at I, let's say. And then then my whole thing could be I can make dp at I at c the maximum score I can get. Sorry, like pretend I have my array and like this is index I. So dp at I at c could be the maximum score I could get in this region up to and including I if I make this choice C at I. So then the idea is I want to compute dpi at C from dp I minus 1 at 0 and dp I minus 1 at 1. So, sorry, the idea again to really say it, I guess, is that the best answer up to and including this point, so using values just up to this point, can be achieved by getting like either the difference to the maximum and like the best value I can get going to the maximum, or the difference to the minimum and the best value I can get going to the minimum. And then we repeat that twice because there's the choice I choose to maximize my current spot or minimize my current spot. And then it just becomes a DP. So this might make more sense if I actually implement it too. So let's actually do that. So first thing we do is delete the sample code. Then we're given some number of test cases here. So we're given T test cases. So first thing I'm going to do is read in T. Then I iterate T times. For each T, I read in the size of my array. And I read in my array values. Okay. So now I want to make this like weird like 2D DP array. So the idea here, I want it to be a 2D array. So I'm going to build it with a list comprehension here. So it'll be, let's see, I'll just default it. So I'm just allocating the memory for this array first. So I'll just assign the values to 0, 0. Doesn't really matter right now. I could put like any values in here and it would still work. And I'll say for I in range n. So that means I'm going to make it like n elements long. So one actual cool gotcha here, this is a really nifty gotcha. If I didn't do this with a list comprehension and I instead just did this, this would seem to work. And let's actually do this here even, because it looks really like it should work. Oh, sorry, not 5, it'd be like n. But regardless, let's try that with 5 in here just for fun. So if I did like, I tried to make a 2D list like this, and I said times 5, I would get, oh, sorry, let me do this. I would get this nice looking 2D list. But this 2D list has a really interesting quirk, being that if I go like array at 0, 0 equals 1, you see it actually gets updated in every single element. Because when I multiply this array element here, it's copying like the exact same element. So it's pointing to the same thing in memory, which is really bad. Because that means like I can't access these things independently. Like it's the same memory repeated over and over again. So to avoid that, we can create this instead with a list comprehension. So we go 0, 0 for I in range, and like this would be n, but I'll do 5 for this example. And now if I do like a at 0 equals something, you'll see it just sets that one. It doesn't set everything else, which is what we want. So that's why here I do for I in range n. Okay, so now let's do our base case. So our base case is actually really easy. I say do our base case, we actually don't have to do anything for it since we initialized to 0. So our base case, since dpi at c is the best answer up to I, so our base case is when I is equal to 0 here. So the highest value we can get up to here is actually just 0, because I have no elements before here to take like a difference with or anything. So we'll just have 0 up to this point. So then, I guess the only hard part now is we have to come up with a recurrence to calculate all the rest of the DP values. So what do I know off the bat? I know off the bat I'm going to have to calculate the DP values for 1 through to n minus 1. Since I've already calculated DP at 0, and I know I have to have my DP value for every spot. So let's go for I in range 1 to n. So I guess always good to remember range in Python is inclusive exclusive. So it'll start at exactly at 1 and will go up to, but not including n. So this the largest value I will ever get is actually just n minus 1. And now let's consider computing one of our given values. So if we do dp at I at 0, let's ask ourselves what this represents. So dp at I at 0 is going to be the best value we can get up to index I if at index I choose a minimum element. So then now consider if, here, actually, let's draw this. So let's say my current, so let's say we're in our array, and I'm going to draw these as like almost like a stock chart or something, I don't know. Let's say this is my current I, and let's say up here I've shown like b of I. These are b of i's for you guys. So the thing we're trying to compute right now is dp at I at 0. So that's to say dp at I at 0 is what's the best value I can get up to I if at I select this bottom value, which is like 1. Since like 1 is the lowest value we can choose. So I guess there's 2 ways we could get to this. We could get the best answer here, right? So I know on my previous thing, I either chose 1 or I chose the max thing. So my best answer here is either the difference between me and the other guy here, which is 0, since we're both 1, plus the best answer I could get up to this point. So the best answer up to I minus 1. Or it's the difference between me and the previous b at I. So that's to say b at I minus 1. So my difference there, plus the best answer I could get up to the b at I minus 1. So let's actually write that out in code. So I said it'll be the max, the best of either going to the previous guy. So we said this previous guy here. Oh, sorry. I'm using Control Z in 2 windows. It's not working out for me. Okay, sorry. So if I go, if I'm doing 1 here, which is what we're doing for dp at I 0, and I did 1 the last time, then the difference would be 0. So we don't have to worry about that. But we also have to add the best answer I can get up at the previous, the best answer I could get to the previous point, which is dp at I minus 1 at 0. Now, if instead I got to this, my best answer here by being a maximum at this I minus 1 point, then the difference would be the value at that maximum. So that's, I don't want to call this A, I'm going to call this B. That makes more sense because it is the B array. Sorry. So I'll go B at I minus 1, minus 1. So the difference between 1, which is my value, and B at I minus 1, which would be the previous value, plus the best answer I could get up to that point, taking a maximum. And give myself a bit more space here. There we go. Okay. Now, the max is sort of similar. We can draw it out, like quite the same. So for the max, consider, so instead of being on the bottom like we were for this guy, let me erase this. For the max, we're going to be on the top, up here, and we're saying, what's the best value I can get up to index I if at index I chose b at I chose like the top value. Well, to get here, I either had to be on the top value on the previous one or on the bottom value on the previous one. So let's start with bottom, since we started with bottom on the last time. So then for bottom, I get the value of the difference here, which is going to be my value minus 1, which would be, it's the lowest value, right? So it's the value of the bottom for the previous one, plus the best answer I can get if I went to the bottom on the last one. And so we max that with the option that I go to the top one, so me to the top one, in which case the difference is the difference between me, my top, and the previous top, plus the best value I can get going to the max at the previous one, which is this. Nice. And now that should have given us our dpi at 0 and dpi at 1. And so our final answer, if I know the value up to some index I, then the value up to the index n minus 1 is the best answer for my overall array. So my best answer is actually just the max of like dp I at 0, sorry, dp n minus 1 is 0. So the best answer over my overall array if I end on a min, and the best answer in my overall array if I end a 1. And we'll notice dp at n minus 1 is already a list, so we can actually just write that as this equivalently, which is a lot cleaner. So let's try that out. So I think this works. I want to point out too, since I think this actually might mean we're done. So this is really what DP boils down to. So you saw we broke the problem, like we broke like solving this across the entire array into an easier problem, which was solving this for like part of the array, and eventually like broke that down into a base case, and we're able to build up a solution using this thing here called a recurrence. So this is all dynamic programming is. You'll see like our solution is really short, like it's like less than 10 lines. So in dynamic programming, these problems tend to be very easy to implement, but they tend to be difficult in the sense that you need to be able to come up with these recurrences and figure out like what you want to do your DP on, and like that's like not necessarily intuitive, and that takes a bit of practice. And so I guess I already showed it once, but highly recommend this like @coder educational DP contest because it goes through some like pretty easy DPs to some fairly difficult DPs. But let's actually submit this and see if this works, because it'd be really funny if I did my spiel and then we got the wrong answer. Okay, we're waiting, processing, and moment of truth. Okay, oh, one more. Oh, okay, cool, we've solved them all. Okay, so that is a correct solution to the last problem. So you saw just dynamic programming. You don't need that much code, but it's really pretty to think about. I hope you guys enjoyed all of that. And I guess this is the last contest in this format. Congrats again to our winner. And I hope you guys enjoy some of our workshops in the upcoming weeks. Peace out.